Hello.
1, 2, 3, testing.
Yeah, can everybody hear? Fantastic. Cool. You're on.
Okay, thank you. Hi folks, I'm Dave. Hope you're all suitably caffeinated after your break because I have a lot of stuff I need to get through in this session. Don't worry about taking photos or anything like that. Slides will be made available after the session. And sorry I'm not actually with you today. Combination of limited travel options into London and train strikes kind of got in my way. So all about containers and containers on AWS. So containers have a relatively illustrious history. Docker sprang on the scene about 6 years ago and everyone went, wow, this is cool. But obviously they actually have been going back to mechanisms of isolating runtime environments within operating system instances all the way since Unix v7, and there's a reasonably straightforward lineage from there to containers as we know them, with some interesting offshoots like Solaris zones. Yes, I used to work at Sun. In terms of how they actually sit together, I assume this is something that you've probably mostly seen before, where you where you can compare and contrast your classic single OS with multiple apps running on it to guest OSs on top of a hypervisor, often running a mix of applications, but normally one principal application, and then moving to containers where you have a separate abstraction layer in that actually abstracts you separate runtime environments on top of your operating system. We've actually done something slightly different again in our Firecracker environment, which is available open source on GitHub, in that we've pretty much got rid of the OS layer to enable you to run containers straight on top of a hypervisor with some extra I/O on the side. If you want to look at Firecracker, we've open sourced the thing. It's an interesting project to go look at. And we actually use it both on our Lambda environments these days and also our Fargate environment. So when you're running containers, there's all sorts of things that you need to look at as distinct from operating systems, in that the little runtime environments and application versions tend to change more often. They pop up, they go away, people auto-scale them, and if you're looking, and most people use containers for delivering microservice style environments, so there's a lot of dependency meshing going on. Obviously, as mentioned, you're normally sharing an operating system, which means you're sharing an operating system kernel and also networking and also a networking stack to go along with it. And there's different ways of addressing this, which I'm going to be going into. Now, in AWS, you've got a few options. So ECS is just essentially our version of Docker. You can run that up on either EC2, which is just a regular hypervisor-based operating system where you're root, or you can use a new service that we've got called Fargate, which enables you to just actually run containers themselves, and we look after the operating system. So the big distinction is that on EC2, you get to actually choose your operating system base image and configuration around that. Fargate, we do that bit for you and just look after the container. The second option for orchestration is Kubernetes via our EKS service. Again, you can run that up on EC2. You can't actually get Kubernetes management on Fargate yet. We actually are working on it at the moment. And the reason why that's got a number 32 on it is that we've actually made our containers roadmap public. We've actually put the thing up on GitHub. Obviously, with all the work that we're doing with the likes of the CNCF, taking their output and also the Kubernetes project's output and building it into our services, they make their roadmaps available. Our containers team decided that it made sense for them to as well, just so that everyone can see how everything meshes together. So you've probably heard a bunch of stuff around this thing called Kubernetes. It's originally a Google project. It's now got very much a life of its own. It's a not exactly simple thing for actually managing and handling containers at scale and how they are able to sit together and talk to each other. Comes in two pieces, essentially, control plane and data plane. The control plane is a whole bunch of applications primarily written in Go, which Google, I understand, actually wrote in order to write Kubernetes in. And then you have your data plane, which is where you have your individual nodes and then where your workloads go running in pods. Now, on EKS, as I said, the control plane is a large and complicated thing to manage. So with EKS, we've actually taken that piece away and we look after it ourselves. You just need to worry about the containers you want to run and standing up the hosts in your data plane to actually run it on. Our control plane, as well as having gone all through all the Kubernetes conformance tests, is also run in a manner so that it meets all these requirements that we have audit reports against. So if you're running in a regulated environment, this may be of use to you. So as I said, you need to, in an EKS environment, look after the handling and management and building and life cycle of your containers themselves, and also the provisioning of the hosts that you actually run on, you run that code on in the data plane. So if you're a developer actually putting together a container, what you need to do in AWS isn't that much different to what you would do in any other context, but there's some extra tooling that we can bring to bear. So first of all, your base actual image, they get identified by tags, they get stored in repositories, they get organized in registries. And let's take an example here. Let's take a look at an Nginx container. So normally you'd go looking for one of those. You'd pick up the latest image. That'll go in a library, and you'll get it from somewhere like Docker Hub. And these actually look not entirely dissimilar from our own resource name identifiers. So your containers all live in registries. Some of these are managed by the likes of the nice people at Docker, some of which you can actually manage yourselves, like our own Elastic Container Registry, ECR. Some of them are open source, some of them scale to enterprise, and if you're using your own register, you should be able to put controls in place so that you can trust what gets put in it, so that when you actually want to go taking a container and running it, you can pull it from your own repo, which is going to be close to where it needs to run, and then actually just stand it up. Public repos, I wouldn't trust what's in them myself. There is some scanning that gets done on them, but the nature of the scanning isn't necessarily that open. Also, you don't know how frequently scanning happens. There have been some interesting things found in images that people have got from Docker Hub before now, although they are working hard to clamp down on things like malware in containers as it is. If you go to commercial repositories like the Docker store, obviously that gets submitted by vendor partners, goes through further verification process, and as Reagan popularized an old Russian proverb, trust but verify. So to go about containerizing an app, let's actually see how you go about doing that. So if again we take Nginx, we go to Docker Hub, there's our latest repo. We can see that it's built on top of the slim version of Debian Stretch, which has most of the stuff in there is stuff that you're likely to need, but there's probably some things that you don't. In terms of how to go about selecting an image, we'd recommend actually avoiding the latest tag because you still don't know what actual version latest is. So when a new version gets cut, that inherits the latest tag. You've actually changed a version and you don't necessarily know it. Also, if you're doing security scanning on your containers prior to deploy, that may cause issues with your scanning tools. So always best to actually use a tag of a numeric. If you're building your own containers, build from scratch is the ultimate minimalist approach, in that your container actually starts off empty, and obviously with nothing in the container, there's nothing there to compromise. A lot of people use the Golang option because you then wind up having your binary as a single file with everything statically linked into it. It's kind of the container version of a microvisor. So with your containers, unless this is really important, actually, there's a couple of thousand containers that were found on Docker Hub not that long ago that didn't actually specify users. So this means they run as root, which means they get privilege on the underlying OS as well as the container itself, which is bad. So be sure your container has a user. Obviously, you need to ensure that your code is security minded. You don't want to go hard coding any credentials into your containers, and we actually provide some tooling that helps with that. We've got two options. One is Secrets Manager, the other is Parameter Store. Each can take a secret, whatever your credential may be, of up to 4K in size, which is plenty large enough for an RSA 2048 private key. Obviously, you want to go putting your containers through a CI/CD process, which includes application security review. You can also use our encryption SDK and indeed other AWS SDKs to enable your containers to go making AWS API calls, which is what you're going to need to do in order to use Secrets Manager and Parameter Store. So to use Parameter Store as an example here, if you give your container, whoops, that should actually be ECS there rather than Lambda. Typo on my part, I can fix that afterwards. If you just give it these parameters and ensure that it has this policy, then you're able to actually use Parameter Store to go and take an RSA private key that's been put into it, encrypted using the secure string flag and KMS private key with this key ID, and actually go substituting it into a shell command where the contents of the curly brackets here get expanded out into the key, to then go retrieve the key, put it in all the places that you'd expect Apache to want it, and then you can go start your server up again, it doing this based on whether the entity is tagged as a web server. When you go about actually building your containers out, each Dockerfile command is an individual layer. There are ways and means of reducing them. You probably don't necessarily want to go maintaining multiple Docker files unless you're building multiple versions of a containerized app that's using the same tooling. Again, this is where you may want to have different Docker files to actually take out debug tooling, so you're running a minimal image in production. You can do multi-stage builds on this, or you could actually build without Docker at all using other microvisor tooling. Obviously, in the deployment process and also in the build process, people make mistakes, so there's ways and means to deal with this. And in terms of automating continuous integration and continuous deployment pipelines, this is something I actually covered in my presentation at last year's AGM. If the slides are still online, that's good. If not, I can send a link to another version to incorporate. So normally, you just take your source, you'd build it, you'd store the image. Obviously, at your source, you have the opportunity for doing static analysis and linting of your code. You can scan the image in the pipeline via a test phase, also do things like automated penetration testing there if you want to, and then sign the image and then go and store it. We don't actually have any cryptographic signing tools ourselves in ECS and DKS, but the regular Docker ones can be imported into your pipeline and they work just fine. In terms of integrating scanners for build time, there's a bunch out there in the world. Claire is open source. Twistlock and Trend Micro are available in the AWS marketplace. There's also runtime scanners. Aqua is also available in the marketplace as well. And here's a few more container-focused AWS marketplace partner solutions offerings. So you've built your container, now you're in ops, your friend in dev has just sent you a new image. What are you going to do with it? Check the file from the source, validate the build pipeline, check the scan results, and go make a runtime. So this is where actually, in terms of a shared responsibility model, development and operations meet each other at the runtime configuration. So what the runtime actually looks like is it's just a set of instructions that tells the scheduler how to go running containers. So for regular Docker, it's a task definition. Kubernetes, it's a pod spec. In terms of what you can do to add security to this, when you start looking at the kinds of capabilities that you have in SE Linux, most containers clearly don't need root. You don't want them having root. You don't need to SSH to a container. You would just take the container away and build a new one, and go and actually do any evaluation of what might be going wrong as in a scratch image in the build cycle. So you can actually go dropping unnecessary capabilities. Docker drops a bunch of them for you. And this means that should somehow your application get compromised, it reduces the ability of your attacker to do anything useful. Namespaces are used primarily for separation of sparse resources like process IDs and network information from between different containers running on the same base image, in order to actually prevent unnecessary communication to do them. Docker uses namespaces extensively, and it's one significant part of container isolation. This also is what the main thing that it's done relatively recently is actually give you sparse user IDs. So you can have user IDs that are effectively the same across multiple containers, and they don't wind up mapping to each other. C groups came out of SE Linux primarily for limiting the ability of containers to access hardware, and also their ability to use hardware as a means of covert channel communication between each other. So you can use C groups to further isolate your containers from each other, and also set resource limits so that you don't wind up having one container taking over the whole physical capability of a machine. So again, this is something that Docker does by default. You can tune it as you need to with soft and hard limits. Hard limits you'd normally set down at the operating system level. Soft limits are things that containers can be given privilege to tune themselves, such as being able to scale by increasing the number of processes they're able to launch. What you want to do there, of course, is by limiting the number of processes, it stops an attacker actually compromising an environment and causing it to go and fork bomb itself. So you can do fork bomb prevention by limiting process count. Setcomp actually further enhances what you can do with the SE Linux limitation and also C groups by further taking away the ability to make specific system calls. Default profile takes a bunch of them away. You can take more away. Again, this is something that you can get into in more detail. You'd normally run your containers unprivileged, so that they can't go accessing the underlying host. It winds up, it's there for some very limited use cases. Most people don't need to run Docker in Docker. So this is something that you can get. This is something that you can get rid of. Run all your containers unprivileged. Similarly, for the most part, if you're working in an environment where you're storing your persistent state in a back-end database, so your web server containers and your app server containers are effectively stateless, you can normally get away with actually setting your containers to be read-only, and then actually just using stood-out and stood-air and piping those to remote logging capabilities for actually writing your log output. We've already mentioned briefly what you can do about putting IAM roles and permissions on your containers themselves. You can also put them on the underlying instances that you host your containers on if you need to. But normally the usual thing is to put them on the containers themselves to give you a least privilege environment there. If you're doing this on Kubernetes as opposed to ECS, you do need an additional daemon linked to it down there at the bottom in order to map IAM permissions and Kubernetes permissions together, but more on that later. Also, of course, it means that if you're dealing with permissions on the containers themselves, then you don't need to have shared permissions on shared permissions inherited by a container that happens to be running on the same underlying server. Network security, when you're down at the actual host level, your network traffic is bridged. So you wind up getting data coming in that is potentially visible to all containers, and you wind up separating this out by having a network abstraction over and above that by having routing to individual containers and further isolation that you can manage with security groups and virtual network interfaces as we've got there. So as you can see, we're able to filter traffic at the container level. Again, you wind up using a plugin in order to do that and effectively act as a virtual router. So if we get below the containers themselves and look at what you should do to protect your operating system, everything that you do to protect a traditional operating system environment in a cloud applies. But in container space, obviously you want to be running minimal images that only have the capabilities to stand up and run your containers. I rather like what comes out of the Atomic Linux project because this actually uses SE Linux profiles to do further separation assurance between your individual containers at operating system level. So all the best practices that you would do for operating system management apply just the same on ECS and EKS as they would in regular EC2. All the same protections work. And rather than actually going and patching your instances, it's far easier in an environment where you're standing up and destroying containers regularly to also stand up and destroy your instances. So make your EC2 instances immutable and stand them up, tear them down, and configure them as per your Docker security recommendations from CIS and others. Of course, if you don't want to go actually doing operating system husbandry, we can actually do that for you with Fargate, and there are good reasons why you'd actually want to do this, particularly in a Kubernetes environment, which I'll get onto in just a little bit. So in terms of container deployment, you can either do it yourself, but obviously, just as with development, you want to go about automating this. So a lot of people do it with CloudFormation, to actually go and push your containers out. But again, those CloudFormation tools need to be called manually. So it's best to actually incorporate it onto the end of your CI/CD environment by using code pipeline that then just goes and calls the runtime environment itself to deploy your container once it's built and tested. In terms of actually managing your orchestration tooling, this is where we get into how what Kubernetes does can be made to integrate into a regular AWS world. So we've got our identity and access management system, IAM. This integrates just readily as it comes with ECS for regular Docker on AWS. If you're running Kubernetes, it's got its own IAM mechanism with its own Kubernetes role-based access control system, and you need to integrate the two. What we've actually done with EKS is when you go running a kubectl call against your Kubernetes control plane, that passes your AWS identity, and EKS actually then goes and verifies that against IAM to verify the genuineness of the identity before also then go and verifying against Kubernetes RBAC what the permissions that that identity has are, before then determining whether you're allowed to actually run your kubectl or not. So there's an integration on the back end there. Kubernetes RBAC roles don't look that far different to what you'd expect in IAM. You can define them yourselves, of course, but Kubernetes does come with some relatively broad brush ones that a lot of people tend to pick up and modify, and essentially use these as a baseline to develop from. In terms of assigning roles to tasks and pods in terms of where your runtimes go, from an ECS perspective, you can just bind an IAM role to your underlying instance or to your container, and it'll just work. If you're using Kubernetes, you also need to add either kube to IAM or KIAM, both on GitHub, in order to make that work. So these are the roles that you would wind up assigning to your different nodes and pods based on privilege requirements to enable them to go accessing the various AWS services that you may need them to. So again, you can do this either with roles on the instances themselves or on the containers.
Hi Dave, it's Lee. Just starting to run out of time a little bit now. Is there any other key messages you'd like to get across at this point?
Yeah, just a little bit. I'm nearly done actually. Logging, you can do CloudWatch logs out of Kubernetes, although you do need to turn it on manually. You do need to configure both Kubernetes network policies and security groups. But security groups can give you the ability to further microsegment. EKS by default makes your control plane endpoints public. You want to specify that they're private by default. And also, when it comes to separating workloads, you may actually want to go running entirely separate clusters for separating different layers of workload. So as Kubernetes itself gets updated pretty frequently, we can do that for you. We can deal with the heavy lifting on that if you run EKS, and also you don't need to update your nodes so much if you're running on Fargate. The cluster separation mitigates risks around certain security issues that have happened with Kubernetes in the past, and I've already mentioned what you can do with parameter store and secrets manager versus Kubernetes secrets capability. You can't use Kubernetes own secrets outside of Kubernetes, whereas you can with the other two. What you do get, which is really neat, and unfortunately I don't have time to talk more about with Kubernetes specifically, is admission control, but that's something I'm going to need to leave for another time, unless you want to go reading up an open policy agent, which is one of the neater ways to actually do that. Essentially doing sanity checking and pre-filtering and mutation of API calls to the Kubernetes control plane when you make them. Essentially acting much like a slightly turbocharged IAM purely for Kubernetes. In terms of the projects that we have sight of and are a little bit involved with, these are all different container security toolings that CNCF and others do. And phew, I'll leave it there. Thanks.
Good evening.